we're going to bring the meeting to order.
Yeah. I want to hear about this.
Does that mean make it louder or you're doing good?
Okay. Louder.
Just kidding. Okay, so that was a fantastic show with our new projectors in there. Very sharp. I'm looking forward to some very good shows in the future in there. So we have tonight a very special, a friend of mine, a colleague from Santa Barbara Research Center, who worked on JWST, and he's going to give us a talk tonight. The Baron will introduce him formally in just a moment. But before we do that, we have our commercial from the merch manager. We have all sorts of paraphernalia, and of course the coveted SBAU coffee cup, which you get free if you give a talk up here.
Some of you probably recognize me from the front door. There's many hats. One of my hats is, like Jerry was saying, is the commercial tonight. I am the merchandise manager for our club, and we have all kinds of goodies. This one I wanted to bring because many of us are traveling this year, or this summer, and this is such a cool bag. It's got, after TSA, you can put your water bottles in here, and then it has a pocket up front, and then it has a deep zippered pocket inside. And if you're a member, they're only $20. If you're not a member, they're $1,000. If you are a member, then they're $25. So I will be in the back or the front or wandering around. So see me, find me, and we can go. Yeah. You're right. Okay, Robert. And Robert is reminding me, I have 2024 calendars. I know it's August, but get them while they're hot. They don't need batteries. And they have some really cool pictures. These are from the Astronomy magazine. And Dr. Love is going to show us all the James Webb pictures. This has other pictures. So I've got one that's open up here. And these are for the same price for anybody. They're $10. So they're available there. And then, as Jerry was saying, we have the coveted AU coffee cup. And like I was also saying, we're giving that to our speakers tonight. And I do have a couple with me, if you're interested. So, and then my other hat is, I am co-secretary for the club, and we have membership forms up here. And we have, well, the outreach coordinator will also tell you about what's going on here. So, okay.
Thank you, Matt. And now we have a rundown of our outreach for the month of August, given by Chuck McPartman, our outreach coordinator.
Okay, busy month as usual. Tomorrow night's Kachuma Lake, starting at 8. There's a slideshow and then telescopes in Dakota Plains. If you're not a camper, I think they're going to charge $10 a carload to come in, but otherwise stuff is free. Then every Thursday, we set up at 7, but starting around when it gets dark, we're at Bacara on the Angel Oak lawn out there, the bluff top lawn, overlooking the ocean, nice and dark, and lots of interesting people. And then on Friday the 11th, we're at Refugio State Beach. Then on Saturday the 12th, second Saturday of every month, is the Museum Star Party here, weather permitting. We usually have 10 or so telescopes set up, and then there's the observatory open with the 20-inch scope. And then on the 16th, we're at Carpinteria State Beach, Wednesday the 16th, with slideshow and telescopes. The 18th, the third Friday of every month, is Westmont College at their observatory, their public telescope night. 19th, we're back at Kachuma. 22nd, fourth Friday of every month, is Telescope Tuesday at Camino Real Marketplace. There's a lot of light there, so we make sure we got a first quarter moon to look at. So that starts at 7. And then on the 25th, Friday the 25th, we're at Refugio State Beach again. On the 26th, we're back at Kachuma, and that's it for the month. And there's plenty of propaganda here. We have star maps, we have moon maps, we have web page listings. We have a more primitive version of the sign-up sheet to join the club. So if we run out of the more formal ones that are here, you can use those. And we have tons of bookmarks. So feel free, don't be shy about grabbing those. And we've heard on good authority that they'll even work on a Kindle if you have a piece of blue tape. So, thank you.
Thank you, Chuck. And now, Ron, where are you? Oh, there you are. Okay, Ron will be taking over and introducing our speaker.
Thank you for dressing up, Mr. President. Viva la, there's some holiday around. Hold on, have you heard about it, Peter? Something we're doing out there in the streets. I wanted to plug a couple things before I introduce this amazing man that just joined us. And he's been coming to the meetings. And I gotta tell you, we would not have been able to hold this crowd down in Farron Hall, would we? I'm starting to like this place. A lot of room, chairs you can move. It's just down there you could instantly sit with somebody. It was very intimate down there. Did you ever go to Farron Hall? Did you? Well, I got a couple things I want to plug real quick before I bring Dr. Peter on, Dr. Ray. Let me get my glasses on. We have next Saturday, of course, the Star Party is at night, and they're well attended. We have hundreds of people showing for that, families, new people, future members of the club. But we also have a planning meeting that if you're a member of the club, you might want to join us through Zoom, check with somebody in the club, the pres, and go on the screen with us. That's 3 hours earlier, every second Saturday of the month. In this case, it'll be the 12th, I think, next week. We also have a Monday morning podcast, which is not a podcast. Well, it is a podcast if you listen to it. It's a vlog, meaning you can see our ugly faces. We're in talking heads on the screen, 11 o'clock every Monday morning. It's called, if you'd like to watch it and join, you can even join us and leave messages, ask questions. Go on YouTube, 11 o'clock every Monday morning, and look up SBAU Astro Hour and see program number 129. 52 weeks in a year. We've been doing this over 2.5 years, and I don't think we've missed a program. I myself missed one, and I think the president was out of town once, but I think it's been every week, and we have a grand time. In fact, most of the guys that are on the screen are here, I think. Bruce Murdoch I don't see, but I did see Tom Whittemore. Is that Bruce? Okay, how about Tom Whittemore? Are you here? Ex-Westmont, he was in the auditorium down below. He was in the planetarium. Anyway, join us online at 5 if you think you'd like to take part and contribute to our planning meeting, the same as a board meeting. And I'm going to tell you right now, we've got the next 2 months booked with speakers. September 1st, which is the first Friday of next month, it'll be JPL NASA, well-respected scientist, who's a very friendly guy, incidentally. He's bringing a whole bunch of friends and family. I've invited him to come join us and watch the show before down in the planetarium. Dr. John N. Callis is going to do a report on this very stage called The Dark State of the Cosmos. Ooh. And then on October 6th, we have a world-renowned columnist for Astronomy Magazine, Skyman Bob Berman, with a Zoom talk. So we'll see his face and then everything else, and I hope the sound is right. His program is called Where is the Universe? And I believe it's about things that have changed since 1995, new discoveries that are changing everything in astronomy. And there's even a new one involving the web you might be bringing up tonight, maybe not. It's also very controversial. Let's find out about this guy. He's raring to go. He's an old friend, as you learned, of our president, born in Toronto, raised in Arizona, age 12. He moved to Corona del Mar, attended UC San Diego, earned a BA in skateboarding, spent his junior year at the University of St. Andrews, Scotland, Milan, where he learned to kayak surf on the North Sea. If you can tell us about that, please. Graduated UCSD and eventually got his doctorate in solid-state physics, following a brief postdoc postdoctoral hiatus at, of all places, the Naval Weapons Center in China Lake, he returned to Santa Barbara and worked at Hughes Aircraft, which I guess became Santa Barbara Research, or sold it, or...
It was owned, SBRC was owned by Hughes Aircraft.
I used to have a mobile DJ service, and I would do Santa Barbara Research's yearly parties. They were the wildest crowd of break dancers you've ever seen in your life. In any event, let's bring him on. In 1999, Peter worked on the mid-infrared detector, something about the new telescope he's going to talk about for the Webb, which was launched years later, 20 years later. So let's have a big hand for Dr. Peter Love.
Yeah, okay. Thanks, Ron. Well, that was refreshing to see the new projectors in the planetarium. Breath of fresh air, but not literally. It was quite hot in there. I'm excited to tell you tonight a little bit about the James Webb Space Telescope. Chrissy Cook, who no longer works at the museum, but John has taken over for Chrissy. Chrissy, are you here? I don't think she's here. She gave a talk on the James Webb Space Telescope almost a year ago, I believe. But a lot has happened since then. We recently celebrated the 1-year anniversary of getting actual science data from the Webb telescope. So, James Webb Space Telescope was originally called the Next Generation Space Telescope, NGST. And I think it was renamed in 2002 after the second top administrator at NASA, you guessed it, James Webb. And he was administrator of NASA during the Mercury, Gemini, and the beginning of the Apollo era. So that's where it got its name. And there's some controversy about that right now, but I'm not going to get into that. As I hope to show you, the James Webb is a very complicated telescope. A lot can go wrong. It's actually a complex machine, is the way I like to think about it. A lot of things can go wrong, and amazingly enough, nothing did go wrong, and I think that's a very good testament to the thousands of people who worked on it and worked together to accomplish something together. So I got involved with JWST back in the mid-1990s with some of my colleagues who are here tonight that worked on it as well. Could you guys stand up? I know Alan Hoffman is here, Roger Holcomb is here, Ken Ondo is here, anybody else who was affiliated with our astronomy program at SBAU. So it turns out that all of the detectors for JWST were built within a 60-mile radius of here. The mid-infrared detectors for the mid-infrared instrument, MIRI, were built by SBRC. That's what I worked on. And the near-infrared detectors were built at Teledyne Imaging Sensors, or Systems, I forget which. They keep changing the name. Back then, I think it was Teledyne Imaging Sensors or something like that. And that's down at Camarillo. So they built the detectors for the near cam and the near spec. And I'll explain what those different instruments are in a few minutes. So first, I'm going to tell you a little about the telescope overall, what it does, why it's groundbreaking for astronomy, or maybe it's space-breaking for astronomy. A little bit more about some of the four major instruments on the observatory, and then I'll delve a little bit deeper into the mid-infrared instrument, just to show you how complex this thing is. And then finally, the really fun part will be at the end, or midway through, when I'm going to show you a bunch of images from the James Webb Space Telescope. And I want to stress that images are pretty, and there are a lot of incredible images that we can learn a lot from this, coming down from this observatory. But another big part that I'm not going to talk about is spectroscopy. That's where you spread light out into different wavelength bands. And the problem is spectrographs aren't very fun to look at. They're not very interesting unless you're really a spectroscopist and you want to study all the chemical fingerprints in the spectrum. So the images are formed by combining different colors in the infrared, which we can't see. Infrared is heat. We see infrared as, we don't see it at all. We feel it as heat. And so how do we get images from this telescope if we can't see? Well, we shift the infrared wavelengths taken in different bands in the infrared from about 5 to 25 microns, 5 to 28 microns for the James Webb. We shift it all down to the visible so we can make pretty pictures. And we keep the color ordering, the chromatic ordering the same. That's the only general rule that they follow. So the longest wavelength in the infrared becomes red in the visible, and the shortest wavelength in the infrared becomes blue in the visible. Okay. Webb is the most complex telescope ever put into space, by far. I mentioned that it was originally called the NGST. It was originally scheduled to launch in 2007, but you know how that goes. It was developed by collaboration between NASA, the European Space Agency, and the Canadian Space Agency. It costs an order of magnitude $10 billion to build, way over its original budget. And it took over 2 decades to go from concept to working hardware. As I said, it's an infrared space telescope. If you compare this with Hubble, Hubble was optimized for the visible. It had a little bit of ultraviolet capability and a little bit of near infrared capability, out to about 2.5 microns in the infrared. But Hubble is in low Earth orbit. It's a few hundred miles up orbiting the Earth. So it can't observe something continuously. It only takes 90 minutes or so to go around the Earth, in orbit around the Earth. Unlike Hubble, JWST orbits this funny point, gravitational point called the L2 Lagrange point, and I'll tell you about that more in a minute. James Webb is much bigger than Spitzer. Spitzer was optimized for the infrared, previous telescope that is now no longer in operation. But the mirror on James Webb is much bigger. So, what's it good for? Well, James Webb is designed, among other things, to look back literally to within a few 100 million years of the Big Bang. And as far as we know, our best models today indicate that the Big Bang occurred about 13.7 or 13.8 billion years ago. So we're looking back to find the first stars and the first galaxies forming, the first light. And we can also use infrared to observe stars forming in star-birthing nebula and stellar nurseries. We can study exoplanets and their atmospheres. If an exoplanet goes in front of a star, the light from the star shining through the atmosphere leaves a chemical fingerprint of what's in the atmosphere of the star. And we've actually detected water, carbon monoxide, carbon dioxide, thick molecules of that sort in the atmospheres of exoplanets. We've actually also imaged planets around other stars now. And of course we can study our own solar system. Although we can't study the inner solar system because James Webb has to be very cold. It has to look away from the Sun-Earth system all the time. It can only look to within about 90 degrees of the sun. So it can look at the outer planets, but not the inner planets. So it finally launched, well, it's almost 2 years ago now, Christmas Day 2021, and that was a good Christmas present. So we're looking at for the first luminous glows after the Big Bang, the first stars, the formation of the first galaxies, potentially habitable exoplanets, and the evolution of our own solar system. So, why is it a space telescope? It's much more expensive than a ground-based telescope. Well, it's because it's optimized for the infrared. as I mentioned, it has to be very, very cold. If it were an Earth orbit, it would be too warm, and there are other reasons. The Earth's atmosphere would block out a lot of infrared radiation. Our atmosphere absorbs different infrared bands. So again, we perceive infrared as heat. So these images that I'm going to show you are false, what's called false color images. They've been shifted into the visible, so we can see them. So the heat from the sun and the earth and the moon would overwhelm the telescope and keep it too warm. The whole telescope has to be cooled to very cold temperatures, which I'll show you in a moment. L2 is about 1 million miles beyond the Earth, almost 1 million miles. It's about 4 times the distance of our moon. And as I said, it always looks, JWST, the telescope, always looks away from the Earth, Moon, Sun system. I'm not going to get too technical here, but I just want to show you the electromagnetic spectrum. This is a vertical spectrum. This is a horizontal spectrum, the same thing. And this shows, let me get this pointer, it's pointer. The visible part of the electromagnetic spectrum is just this tiny band right here. Infrared is at longer wavelengths in the 1 micron to 1 millimeter type region. Then we've got ultraviolet over here, and X-rays and gamma rays and so on. So Hubble was optimized for the visible, mostly the visible near infrared, and JWST goes out much further. So 1 micron is 10 to the minus 6 meter, and over here I think the scale is in, somewhere it's in nanometers. Anyway, you can use this to convert microns to meters to nanometers. A nanometer is 10 to the 9 meter. Again, the electromagnetic spectrum, but down here it shows where the James Webb Space Telescope operates, about 0.6 microns to 28.5 microns. Spitzer was actually designed to operate out to longer wavelengths, out to 160 microns. And here's Hubble down here, mostly in the visible. So why infrared? Why did we spend so much money and so many years building an infrared telescope? Well, infrared light penetrates gas and dust much better than visible light does. That's why sunsets are red and the sky is blue. That's due to Rayleigh scattering. So you can see through gas and dust clouds to see new stars being formed, for example, in the near infrared. Firefighters, for example, use infrared cameras now. They've gotten a lot cheaper in the last 10 years or so. Firefighters can use infrared cameras to go into a burning building and look through the smoke and see people inside that can't find their way out through the smoke. They can see the warmth from their bodies, and they can see through the smoke. So that's the idea here. We're looking in the infrared so we can see through gas and dust in the cosmos and see new stars being born. But to me, the most exciting reason that we're using infrared is that the universe is expanding. What does that matter? Well, because the universe is expanding, objects further away from us are receding away from us faster. That's the Hubble law that you may have heard of. So things are redshifted. If you look at their spectral lines, everything is shifted to the red compared to what it would be in the laboratory on Earth. Now, its redshift is not the same as quite the same as a Doppler effect. The Doppler effect is a redshift or a blue shift, depending on the speed of something. But this is a cosmological redshift. This is due to the fact that space itself, or perhaps I should say space-time, is expanding. So as space expands, everything moves away from everything else. It's like raisins in a loaf of bread being baked. every raisin gets further away from every other raisin, and there is no center of expansion. If you were on a raisin, you'd see any raisin, you'd see all the other raisins move away from you. So we can look back further and further away than we can with, say, Hubble, because things are redshifted more and more the further away we look. Now, colder objects such as debris disks, protoplanetary disks around stars, and planets themselves emit most strongly in the mid-infrared. And you can see planets better in the mid-infrared because there's better contrast with the host star. Typically, like in the visible, a planet next to its host star would be totally washed out by the bright star, and the planet would be very dim and too close to the star. So infrared helps with that. You can actually see planets, exoplanets, in the mid-infrared. You also have to use a coronagraph, though, to block out the light from the host star. And I think I mentioned infrared bands are difficult to study from the ground because of absorption by the Earth's atmosphere. And you couldn't even if Hubble were designed to look in the infrared, Hubble would be too warm in low Earth orbit. It's not cold enough. It can't get cold enough. So that's why we sent the Webb out to L2 Lagrange point out in deep space, where it radiatively cools to around 40 Kelvin, that's 40 Kelvin above absolute zero, which you can't go below. I won't get too technical. This is probably the most technical chart I have, so don't worry if you don't get it. But this shows some blackbody radiation curves. Forget about the word blackbody. Planck's radiation law. Usually you see, getting the clicker mixed up with the pointer. Usually these curves, you'll see these curves for very hot objects like our sun, which is around 6,000 degrees Kelvin, very hot. And that's why it peaks, its peak emission is in the visible, around 0.5 microns, or 500 nanometers in the visible part of the spectrum. But I drew these curves to go from, with temperatures going from 40 Kelvin is the green curve, and then the black curve is 100 Kelvin, blue curve is 200 Kelvin, red curve is room temperature, 300 Kelvin. So you notice that the peak of the radiation emitted, like everything emits, your body is emitting radiation right now. Everything in the universe is emitting thermal radiation. But the peak of the radiation depends on the temperature of the object. For a room temperature object, the peak is about 10 microns. Over here, this is Wien's law. You can see at 300 Kelvin, indeed, the peak is at about 10 microns. But if you go down to, say, 50 Kelvin or 40 Kelvin, then the peak wavelength in this curve is more like 80 microns, closer to 100 microns. How does JWST look back in time? Well, the reason we're looking back in time, light did that. We can see back in time because the speed of light is finite, 3 times 10 to the 8th meters per second. That's fast, that's 186,000 miles per second, but cosmic distances are huge. It takes about 8 minutes for light to reach us from the sun. If the sun were to blink out instantly somehow, we wouldn't know about it until about 8 minutes later. So from the nearest stars, it takes light several years to reach the Earth. And distant galaxies are a whole other story altogether. The closest galaxies are on the order of a couple million light years away. And 1 light year is the distance light travels in 1 year at that fantastic speed of 186,000 miles per second. So 1 light year is about 5.9 trillion miles. Distant galaxies are billions of light years away. So we can look actually billions of years back in the past. So, in a sense, telescopes are time machines, especially infrared telescopes, because they can see further away. So this shows what we think happened. The Big Bang happened here, and there was a period called the Dark Ages, and then the first stars started forming here, and the Webb telescope is designed to look back to that point right there where the first stars and galaxies were forming. Hubble is only looking back this far, not quite as far. So as you can see, right today, this is today, the Big Bang, and today, this is 13.7, 13.8 billion years ago. Okay, this is what the Webb telescope looks like. There's a big primary mirror that consists of 18 segments made of beryllium. Beryllium is a very lightweight metal, has good thermal mechanical properties. It's coated with gold to make it very reflective in the infrared. So light hits that main mirror, these 18 segments, gets reflected to a secondary mirror and then back through a hole in this black thing here. This is the sun shield. It's about the size of a tennis court, and it has 5 different layers. And the reason the sun shield is there is to protect James Webb from the sun and radiation from the Earth and the moon. It's always looking into dark, deep space. We've got solar panels, this is the warm side, this is the hot side on this side of the sun shield, this is the cold side, and everything here is radiatively cooled to deep space. By the way, deep space is around 3.7 degrees Kelvin. So you can get things pretty cold if you have a sun shield and just radiate away to space. A little more detail. Solar panels. This thing is called the ISIM, the Integrated Science Instrument Module, and that's where the 4 instruments live. It contains the near-infrared camera, the near-infrared spectrometer, and those detectors were built by Teledyne. MIRI, that SBRC, now Raytheon, built the detectors for. And finally, the fine guidance sensor and the near-infrared imager and slitless spectrometer. So those are the 4 primary instruments. So again, on the warm side, we have star trackers, we have solar arrays to power the whole thing, and this side is all cold. So, how do I start this? Let me just click. This is the deployment sequence. So, the Webb telescope it's big. The mirror is about 6.5 meters across. It can't be launched on a conventional rocket. It had to be literally folded up, origami style, to fit within the fairing of an Ariane 5 rocket. Well, they came up with several ways of doing that, and this will show you how they did that. The sun shield is also, as I mentioned, the size of a tennis court, so it can't fit on top of a rocket either. It had to be deployed. There were a lot of things that had to be deployed, and they all had to go correctly, and thank goodness they all did. So how do I get this to go? Okay. Here it is all folded up. The mirror is folded up, the sun shield is folded up. The first thing to come out is the solar array. Now the sun shield. The tower assembly for the main mirror. The sun shield is starting to unfold. JWST. The whole thing had to be deployed with literally hundreds of actuators and pulleys and pins, and everything had to, I mean, it's like robotically being put back together in space, like a transformer. And there are a lot of things that could have gone wrong, but fortunately, they didn't. How do I get to the next slide? Oh, there we go. So, as I've tried to show you, the web is a very complex machine. Prior to launch, there were 344 single point failures. What's a single point failure? Well, it's something that if it doesn't work right, it could cripple the entire mission. So there were, for example, 155 motors on the backs of the mirror segments, those 18 hexagonal segments. And they all had to be aligned so the mirror operated as one big mirror, not 18 separate mirrors. Every single one of them worked. They all survived. Every one worked. The sun shield is very delicate. It's made of, the layers are made of kapton, and it's light and delicate, and it had to be deployed and tensioned properly. And I think nearly half of all the single point failures were associated with the sun shield alone. But unlike Hubble, which was repaired, what, 5 times now? James Webb is so far out there that it wasn't even designed to be repaired in space. We can't repair it. So it's a good thing that everything is working. This illustrates the L2 Lagrange point where Webb is located. It actually orbits this imaginary point in space. There are 5 Lagrange points, L1, L2, L3, on a line with the Earth's sun. And there are 2 others, L4 and L5, that are 60 degrees behind the Earth's orbit and in front of the Earth's orbit. L1, L2, L3 are not stable. You can't just put something there and have it stay there. So there is some housekeeping needed to keep it there. There are L4, L5 Lagrange points around also, for example, the Earth, the Sun-Jupiter system. Any 2 bodies have these Lagrange points. And if this were Jupiter, there would be the Trojan asteroids are at the L4 and L5 points because those are stable. Okay, here we go again. This is the last animation. This shows the orbit around the Earth. So the Webb orbits the sun at the same rate that the Earth does. It rotates in 1 year, just like the Earth. But it stays opposite the Earth from the sun at all times. So go ahead and play.
The Sun-Earth L2 point is where Webb's orbit around the sun is synchronized with Earth's. At this point, 1 million miles from Earth, Webb is free from the thermal influences of the Earth in all eclipses. Additionally, the Sun, Earth, and Moon, the brightest objects in the sky, are hidden by the deployed sun shield, giving Webb a dark, cold, and stable environment to carry out its mission of discovery.
I think the actual orbit around L2 is bigger than the orbit of the moon around the Earth. So it's not really at the L2 point, it orbits around the L2 point. And the reason it can do that is it's using the gravity of the sun and the Earth together to keep it in that location. So here's Webb compared to Hubble. And in this case, showing also Spitzer. Remember, Spitzer was an infrared optimized telescope. Hubble is not, and Webb is. So this shows the comparative sizes of the primary mirrors in each case. Here's an image comparison of Spitzer to Webb. On the left is Spitzer at about 8 microns in the infrared. To the right is Webb, the mid-infrared instrument, at a little less than 8 microns, but you can see a big difference. You can see a lot sharper images of stars. You can see more stars, a lot more going on. This compares the mirror size for Webb versus Hubble. This is an image comparing Hubble to Webb, and it's flashing back and forth. So right now it's Hubble, now Webb, same part of the sky, Hubble, Webb. So you can see a lot going on there. There's a lot of galaxies and stars. But obviously the Webb images are much sharper. Okay, there's a lot going on here too. This is, again, comparing Hubble to Webb. You can see that the view is sharper with Webb. And notice, you can tell right away which is the James Webb, because in the Webb you get these 6, or there's actually 8, because there's some horizontals. There's a horizontal streak there too. There are these 8 diffraction spikes in the Webb image, but you only see 4 in the Hubble image. Those are called diffraction spikes. They're due to the hexagonal segments on the primary mirror and to the boom, or to the struts that hold the secondary mirror. Now the interesting thing going on here is there's a foreground galaxy, these whitish galaxies. First of all, that's a star. Anything with a diffraction spike is a star. Galaxies are extended objects and don't have the diffraction spikes. So there's only a few stars in this image. That's the one bright one, and there's some others right there, right there. Everything else you see is a galaxy. And this is a field of view on the sky equal to the width of a grain of sand at arm's length. So we're looking at a very, very small field of view, a very small part of the sky. The other interesting thing going on is that the foreground galaxies, the whitish things, are gravitationally lensing these background galaxies, which are much redder. You can see, for example, this guy is really marked, and you can see kind of some circular stuff going on here. And that's these galaxies being, distant galaxies being gravitationally lensed by the foreground cluster of galaxies. I'll show you another example of gravitational lensing later. Again, this is Hubble versus James Webb. You see the diffraction spikes of the Webb are more complicated than Hubble's. You can see more things, more galaxies with Webb. Didn't I show this already?
Yeah.
How did I get here? Oh, I'm holding it upside down. It looks the same on both ends. Okay, let's see if we can get to it. Good review. Okay. This is an attempt to show the light gathering power of each telescope, Hubble, Spitzer, and Webb. So you can see the Webb mirror here. This is to scale the Hubble Space Telescope and the Spitzer. And then on the vertical axis is their light gathering power, and the wavelength range is on the x-axis here. So Spitzer actually went up, as I said, to like 150 microns or something like that, further than the Webb. Hubble went out to about 2.5 microns. So the sensitivity of the telescope is proportional to the area of the primary mirror, which is equal to the diameter squared, proportional to the diameter squared. So Webb has a much better sensitivity because it's got a bigger mirror, but it also has better resolution because resolution is proportional to the diameter of the mirror. However, it's not as good if you put an optical telescope in space with a mirror of this size. It would have a much better resolution than Webb does because Webb works in the infrared at longer wavelengths of light than in the visible. And resolution depends on wavelength as well as the diameter of the primary mirror. Again, the four major instruments: near cam, near spec, mid-infrared instrument, and the fine guidance sensor. So near spec and near cam operate at about 40 Kelvin just by radiatively cooling to deep space. Whereas MIRI has to be cooled to about 6 or 7 Kelvin, that's 6 or 7 degrees above absolute zero. And the only way to do that is with a dedicated cryocooler. Again, this shows the wavelength range of the Hubble. No, it shows the wavelength range of the 4 JWST instruments. The MIRI, mid-infrared, is to the long wavelength and to the right, and everything else is down between 1 and 5 microns. MIRI goes out to about 28 microns. So the difference is that the near-infrared, as I said before, can look through gas and dust at new stars being born. Mid-infrared is good for revealing planets, asteroids, and like roughly room temperature gas and dust heated by nearby stars, as well as protoplanetary disks, which are new disks forming around brand new young stars. Well, here's the hot side of the telescope. Everything is facing, that's facing the sun and the earth and the moon. It's really hot. On the left and on the right is the cold side radiating to deep space. Okay, we're going to look at the mid-infrared instrument for just a couple minutes, and then we're going to look at beautiful images. So the mid-infrared instrument has at least 50 times the sensitivity of Spitzer, 1,000 times better than ground-based. It's hard to do infrared from the ground. Subarc second resolution from 5 to 28 microns. No interference from the Earth's atmosphere. Can do imaging, low resolution spectroscopy, moderate resolution spectroscopy, and has a coronagraph for blocking out the light from a bright star so you can look at nearby exoplanets, orbiting exoplanets. When I said James Webb was complicated, this might give you some idea of how complicated it really is. This is the Integrated Instrument Science Module, ISIM, and it shows the MIRI instrument on the left, the near spec on the right, and the near cam and fine guidance sensor on the top. And I don't know how anybody, I mean, here's a person working on it. I don't know how anybody knows what all these wires and cables and things do. It's just, it's mind-boggling. Here's a cartoon showing the same thing. There are actually 3 MIRI detector modules, focal plane modules. 1, 2, 3, in the mid-infrared instrument. I think this one is used for imaging and for coronagraphy and for low-resolution spectroscopy. And these two here are used in the medium resolution spectrum, for the medium resolution spectrometer in the lower resolution end and the higher resolution end. So there's actually three focal plane modules. It's complicated. This is what a focal plane module looks like. It's got to be thermally isolated from everything around it. It's cooled, and it's got some electrical straps on it, some temp sensors. It's got sensor chip assembly, which is what Alan Hoffman and I were involved in building. There's a detector hybridized to a silicon readout integrated circuit. And Roger Holcomb was responsible for this packaging, the silicon carbide mounting pedestal and the aluminum nitride motherboard that goes right underneath the sensor chip assembly and the rest of this.
Why is there a heater?
Just to keep, if you want this to run at a very stable temperature, you don't want to, to keep the temperature from fluctuating up and down, you want to be able to cool it as well as heat it. That's what it actually looks like. The shiny detector surface is there in the middle, electrical cable.
How many pixels?
1024 by 1024. You've got more pixels in the chip in your cell phone camera than the mid-infrared instrument has. You probably have something like 10 megapixels or more. This is only 1 megapixel. And the pixels are much bigger, 25 microns. The ones in your phone are probably a few microns. But again, we're not working in the visible, we're working in infrared, where the wavelength is at least 10 times as long, 5 microns versus visible 0.5 microns. Wavelength is 10 times bigger, so we don't need little tiny pixels. The green color is an AR coating, anti-reflection coating. This is a exploded diagram of all the pieces that go into it. It's a arsenic doped silicon impurity band conductor detector, silicon readout. By the way, you have to do special things to get silicon integrated circuits to work at 6 or 7 Kelvin. They don't like working at cold temperatures like that. So you have to do special things to get them to work that cold. Okay, finally, we're going to get to images. And what I wanted to remind you, that's why the asterisk is there, that again, a big part of this, the data coming from this telescope is spectroscopic data, which unfortunately isn't very interesting to look at. So I'm just going to show some beautiful images. And remember, these images are in false color. We can't see in the infrared, so everything is shifted down to the visible part of the spectrum. So you saw this before. This is Webb's first deep field. And you see that bright star there with the 8 diffraction spikes. And a couple other stars, and everything else is a galaxy, and there's gravitational lensing of the, by the foreground cluster of the background reddish, more reddish galaxies. This compares the same field of view, the one you just, the object, or the region of sky you just saw, using MIRI and NIRCam. In MIRI, at mid-infrared wavelengths, you don't see as many stars. The stars are not strong emitters in the mid-infrared. This is Stephan's quintet, a combination of NIRCam and MIRI. There are 1, 2, 3, 4. These are interacting galaxies. 4 galaxies. I'm sorry. 1, 2, 3, 4. This galaxy is actually in the foreground. It's not part of this cluster. So let's see. The far ones are 290 million light years away, and the closer one is only 40 million light years. only. This is in the mid-infrared only, without near cam. Looks a lot different. That galaxy at the very bottom almost disappears, but you can see the cores of this galaxy much better in the mid-infrared. But the one down here kind of disappears. So you're getting different information in the mid-infrared than you are in the near-infrared. Cartwheel galaxy with near cam on the left and mid-infrared on the right. It looks kind of more ghostly on the right. This is actually two colliding galaxies, one going through, the other face on. And these spokes on the right, kind of spokes of the wheel, are remnants of the spirals in the galaxy being collided into. Phantom galaxy, this is a mirror image, about 32 million light years away. It's got very beautiful spiral arms. There's a lot of fine filaments of gas and dust. Barred spiral, this shows the Hubble view on the left, and you can see that it looks quite different with the Webb on the right. You're seeing through a lot of that gas and dust, and seeing that the spiral arm really stands out. The Southern Ring Nebula, in the near-infrared on the left and the mid-infrared on the right, this is a planetary nebula. It's a star that has stuffed off its outer layers to form what's called a planetary. It has nothing to do with planets. They're extended objects, so they were originally thought, and they kind of look like planets, so they call them planetary nebulae. But they're actually stars that have blown off in outer layers. The interesting thing here is that you can see a second star in the center, just to the left here, that doesn't show up over here. You can see the diffraction spikes here in the near-infrared. They're much harder to see in the mid-infrared, but you can see this other star. And that other star is actually the white dwarf that they created this planetary nebula. Meanwhile, in our own solar system, this is not Saturn, this is Neptune. Turns out all the gas giants have rings. Jupiter, Uranus, Neptune. So this shows some clouds. So you see some clouds here. These are moons. Here's Uranus, and as John said in the planetarium earlier, Uranus is tipped on its side. Its axis is tilted about 98 degrees with respect to its orbit plane. And you can see some clouds there. You can see rings around it as well. This is one of the poles, polar regions right here. That's a cloud, that's a cloud. Saturn looks, this is a near-cam image. Saturn looks dark because there's methane in its atmosphere, and methane absorbs in the near-infrared. The rings are bright because they don't have a lot of, they're ices and they don't have methane. Some barred spirals that are on the order of 10 billion light years. It took roughly 10 billion light years for the light to get here. They're very distant. You've probably seen this image before. The one on the left is the Hubble image of the Carina Nebula. The one on the right is James Webb. You can see a lot more stars. Near-cam image on the left and a mirror image on the right. And these are right here, these things. Let me show you the mid-infrared by itself. This is the mid-infrared by itself, pillars of creation, and these are young stars here forming on the tips of this cloud of dust. Very beautiful. Tarantula Nebula with NIRCam. You can see a lot of stars in the center there being formed. It's about 161,000 light years from Earth. Thousands of stars are being born there. This is a nebula in the Large Magellanic Cloud, which is a satellite galaxy to our own Milky Way galaxy. Two views of the Tarantula Nebula, one in the near infrared on the left and Miri on the right. You can see a lot of stars just disappear. We've seen that before because stars are often don't stand out in the mid-infrared. They're not strong mid-infrared emitters. Cosmic cliffs in the Carina Nebula with Hubble, and JWST NIRCam and JWST Miri. Again, Miri looks kind of ghostly. This is a protostar. It's got two lobes coming out, and there's actually a protoplanetary disk. There's a little dark band across the middle there, and that's actually a protoplanetary disk within which a solar system is being born. It's a smaller star, 20 to 40% the mass of our sun. It's only about 100,000 years old. It's just a baby, not even doing fusion yet, like our sun. Pandora's cluster, again you see a foreground galaxy cluster gravitationally lensing some very distant background reddish galaxies. And just about everything you see here is a galaxy, except the thing with the bright thing in the center with diffraction spikes is a star. Fomalhaut is a star about 25 light years from us, close to home. And with the Webb, we just discovered that there are several belts of dust around it. The black thing in the center, I think, at first I thought that was due to a coronagraph blocking out the bright light from the star itself. But I think it's actually just saturated pixels. They were so bright they just saturated. Einstein ring. This is an extreme example of gravitational lensing where a very distant star, which is this ring, was gravitationally lensed by this background, or foreground star rather, that they happen to be almost perfectly lined up with the Earth, all in a straight line. And that's why it forms a ring. This is an illustration here of the light leaving the more distant galaxy, being bent by the foreground galaxy and coming to the telescope. And they actually found the orange color here is actually organic molecules, like PAHs, polycyclic aromatic hydrocarbons. This is a hard one to say, I had to look this up. Ophiuchi cloud complex is the closest star-forming region to Earth, only 390 light years away. A lot of stars, well, there's about 50 young stars, about the mass of the sun, forming in this cloud. And some of them, if you look closely, have protoplanetary disks, which means they're forming planets. Herbig-Haro 4647, there are two stars in the center. One's, you guessed it, Herbig-Haro 46, and the other is Herbig-Haro 47. You can't, it's right here in the center, and they're blowing out these two lobes here. They've gobbled up material and they're spitting it back out. So the universe keeps recycling matter from stars into new material from which new stars are born. So what's next? If you look at the previous image, right down here, I don't know if you can see it. that's what we're looking at in this next slide. It's real, just about anything you can imagine exists, and a lot of things that you can't imagine also exist. So what's next? Well, with any luck, James Webb was designed to function for at least 10 years. And with any luck, it'll work well past that, maybe even 20 years. And we're always launching new space telescopes. So James Webb is joined at the L2 Lagrange point by Gaia, which was already there. And just a week or two ago, a new spacecraft got there. What's the name of it? Euclid. Euclid just got there. It's also got infrared capability, although it's got a wider field of view than James Webb. And there are almost telescopes being launched, but even if Webb were to suddenly die today, scientists would have enough data over the past year to keep studying for years. But hopefully it continues to work. Thank you.
Spectrograph, I've never known. Can I just ask one question? You might want to take some questions. Sure. I'm going to ask mine first. And this is something that's never addressed in these space things. That's the radio waves back that brings us the information. They have to pick a place on the lower end of the spectrum in the radio range, don't they?
Yeah.
Either FM or AM or whatever.
It's like I think it's gigahertz type band, but I don't know exactly what the wave band is.
Okay, but
radio the raw data back to Earth. They have a high gain antenna on the warm side of the telescope that points at Earth and sends back data.
every one of them has radio waves coming back or they get nothing back. So what happens if some super jerk in his garage finds that frequency and decides to flood it or hack it? Is that possible?
I suppose it could be jammed to some extent, but we have big dishes on the Earth, and because the Earth is spinning on its axis once per day, we have to use these big radio telescopes all over the world, Australia, Europe, Africa. So the receiving antenna are big, and it has to switch from one antenna to the next as the Earth rotates.
You want to take some questions? Anybody have something? Go ahead. Okay, Mike?
Yeah, I'm here, Mike. Mike, two questions here so that everybody can hear.
Two questions, Mike. Does this work? Hello? Anyway, I'm saying.
There it is.
Yeah, two questions. I'm a little confused about gravitational lensing.
You're not alone.
No, okay. Doesn't it have something to do with bending light or whatever?
Yes.
And then the diffraction spikes.
Okay.
The diffraction spikes, I guess, are endemic to the telescope design, right? But,
Yes, that's correct.
So those two are a little bit
Okay,
cloudy.
well, gravitational lensing was actually predicted by Einstein's general theory of relativity that came out in 1915. He predicted it, and it took a while before we actually had the capability to observe it. But it is lensing in the real sense of the word, because the light is actually bent. Arthur Eddington first showed that Einstein was right by looking at a part of the sky when the sun was not there, looking at the stars, and then again looking at the same spot of sky when the sun is there. During total eclipse, because the sun would blind the light from the stars, and the stars during the eclipse were actually bent in closer to the sun than they were when the sun wasn't there. So he showed that Einstein was right. Now the diffraction spikes, you're right, are due to the design of the telescope. And Hubble had a circular mirror, so it doesn't have diffraction spikes from the mirror itself. but it does have diffraction spikes from some other things that are in the optical path. But Webb has these hexagonal mirror elements, and then it also has a tripod holding the secondary mirror, one of which is aligned, or two of which are aligned with the hexagonal gaps in the main mirror, but one of which causes the horizontal diffraction spike.
It's the struts themselves that are causing the spikes.
Pardon?
The struts themselves are changing the light from the mirror or light.
Yeah, it's a measure of what's called the point spread function of the optics of the mirror.
But you do see diffraction spikes with some of the Hubble images.
Yes,
Smaller.
there are. You can see 4 spikes, as I recall. You pick.
Did you have a question?
The instruments that are on the web are on the cold side, correct?
Yes, all the instruments are on the cold side.
So the entire thing is operated by solar power, which is transferred into, I guess, electricity to
Yes.
function instruments.
Yes.
So how do you deal with the electricity that's going to the cold side to make the instruments work? How do you get rid of the heat from that?
Well, there is some heat called joule heating when you run an electric current through a wire, but the amount of current that the power that these instruments take is quite small. It's very low, so they may have radiators specifically for some of the cabling. I'm not sure, but that little amount of heat that's generated by the electricity going through the cold side is radiated away.
How is it decided what the telescope will be looking at?
Boy, that's a good question. I don't know the complete answer to that, but there's some discretionary time allotted to one group, and then a lot of other groups of astronomers have to compete for time on the telescope, which is very valuable, of course. And I don't know actually exactly how that works. There's a committee that decides who gets how much time. It's complicated.
So it's decided through the government agencies, or have
Yeah,
they
yeah.
farmed it out to like
Yeah,
academics?
through NASA.
Maybe we've got our $10 billion worth out of it already, or?
Well, I think we've gotten a significant part of the 10 billion.
Sure we have.
We'll see. 10 years at least, I hope.
Thank you for your talk and thank you for your work. It's got to be pretty cool being part of the most impressive feat of human engineering in history. One of the things I was thinking about is Webb has already taken a couple shots in terms of micrometeorite impact.
Yes.
Does that keep you up at night, and is that a more existential threat than running out of power to keep station keeping?
I worry about that because already more micrometeorites have hit the primary mirror than they were expecting. It's damaged one of the 18 segments of the main mirror. And there are inevitably going to be more hits that are going to cause more damage. So far it hasn't done too much damage, but that is a concern. I worry about that more than it running out of power.
Hello, two-part question. Hopefully the second one's a tiny first one, but the first one is, what can we expect to see from a very short wavelength of detector versus a very long wavelength? And the second one, second to it is, what would it take for us to get closer to the point of the Big Bang and see what we see at that point?
It would take going further out in the infrared and even a bigger mirror than we have now. We'll never see all the way back to the Big Bang because there was, I showed in that one chart, there was a so-called dark ages in the universe where there was no light that was traveling anywhere. So we'll never see back to the Big Bang itself. The only way we can see the Big Bang itself, well, not long after the Big Bang is the cosmic microwave background radiation. Or gravity. Yeah. Actually, we're now to the point where we're looking for evidence of the Big Bang from gravitational waves bouncing back and forth across the universe. And the way that we're looking for those, and we've found them already, but the ones we found we think are due to merging supermassive black holes, is by timing pulsars. Pulsars are neutron stars that typically flash every few milliseconds. They're very precise clocks. And by looking at pulsars over time, over many, many years, it takes years and years because you're looking for small changes over a period of years because the wavelength of these gravity waves is so huge, it takes years for one wavelength to go past. But by looking at timing of these pulsars, we've actually found some gravitational waves from the far, far away.
Thanks again. How long ago did you freeze your design, and what would you do differently if you had a new shot at it?
The freezer?
No, if you got to build a new one.
That's a good question. I don't know. Build a better sun shield, even better sun shield, so it can get even colder than 40 Kelvin or so. But other than that, you have to have a cryo cooler.
Nothing in your device.
No.
One quick question as far as moving the telescope. I understand that's done by gyroscopes. They adjust the gyroscopes to actually.
Yeah, pointing the telescope is done with reaction wheels. So you turn a wheel one way, and the telescope turns the other way due to conservation of momentum. So yeah, they have probably, I would imagine, 3 different reaction wheels on 3 different axes to move the telescope pointed to different parts of the sky. Boy, we've got a lot of questions here.
Okay. Do you think there's really life out there, and how do you think the James Webb could help find life?
That's an excellent question. They might be here already, I don't know. Personally, I believe there is life. Maybe not like us, but I believe there is life out there somewhere because the universe is so big and galaxies have hundreds of billions of stars and there are billions of galaxies. It would be mind-boggling to me if we were the only instance of life in the universe. The way Webb can help us find it, we've already found some indications. It's very hard to prove that there's life from a distance, very, very far away. But I mentioned that we can study the atmospheres of exoplanets, and we found molecules like water. And we know that for us at least, water is important to life here on Earth. We found other molecules like methane and carbon dioxide. So finding those gases in the atmospheres of exoplanets could be, it doesn't prove that there's life there, but it could be an indicator that there is.
Thank you very much for your presentation. It's really fascinating. I have 2 questions actually. One is kind of maybe it's more detail, but it's kind of interesting for me. Those 18 hexagonal mirrors, are they flat or they are concave?
No, they're curved. They're curved.
To match the overall.
Yeah, so when they're all together and their actuators align them all, it's one big curved mirror.
Alright, so second question, you mentioned those 4 different detectors. Are they active at the same time, all 4 of them, or they need to be rotated and only one of them could be active?
What are you, which are you?
The
talking-
detectors, they are
Oh, the
four
detectors.
different kinds of
Oh.
detectors.
Yeah, I believe they can operate some of the instruments simultaneously, but not everything. It's a little complicated. They can split off the light into different instruments at the same time.
Does JWST answer anything related to dark energy and dark matter?
That's a good question. Well, it does in the sense that we can study gravitational lensing with it, and we know that there must be dark matter, stuff that we can't see, in order for light to be bent as much as it's bent. But a better instrument for studying dark matter is the Euclid telescope that was just put in L2. It's going to study distributions of galaxies across the whole entire sky.
Do you know who's responsible for choosing the colors of these images we've seen? Is there a coloring committee at NASA?
I guess there is of some sort, and different people, there's more than one way to color the images. It's not, there's no single right way to do it other than to keep the chromatic ordering the same. That is, shifting the very long wavelengths, keeping them in order when you go down to the visible. But you could choose different colors for each infrared band in the visible and come out with a completely different image. So yeah, there are a number of people doing it, and it's a fine art the way it's done.
I just wanted to give credit where credit is due here. Is there anyone here from Teledyne? I don't want to step on any toes. The company that came before Teledyne bought them, provided a lot of capital and a lot of administrative help and that sort of thing, and I'm sure developed along the years. But it was Rockwell.
Yeah, originally Teledyne was Rockwell International.
Correct. And they had a long, long history in space with Saturn V. The tiles that covered the nose cone of the space shuttle were developed in Thousand Oaks at Rockwell, their campus. And I just want to give credit where credit is due.
Thank you.
Well, he's taking that around. You worked on the Miri?
Miri, yes.
Is that the one with the big strip of gold or metal at the top, the interior?
I showed you more details of the module, the detector module on Miri, yes.
But you actually worked on that?
Yes.
30 years before it went up?
Yes, and there were times in the past where I hoped I would still live long enough to see it launch.
They didn't give you one on your TV that day, they would give you one to take home and...
No.
What Peter didn't say is that he also worked on the detectors for certified.
A little bit, yeah.
Yeah, and in fact, all of those detectors for all those instruments he was talking about, Hubble, Certif, and Webb, were all made, as he said, within 60 miles of here. They were at Teledyne down in Camarillo and Santa Barbara Research Center, which is now Raytheon in Goleta. And in fact, most of the infrared detectors in the world are made here locally. And I don't know if everybody knows it. You know, up north we call it Silicon Valley. Well, we've been calling the local area Infrared Valley. And it's a really unique area. Just all these infrared detectors for all those instruments, both ground-based and space instruments.
Yeah, this is kind of the infrared center of the universe. Right here.
Okay, we'll just take a couple more questions here.
Thank you so much. Am I correct in, did JWST have any involvement in like its reaches to the 400 million years ago, like the limits of its view shed? Is it discovering structures that are, quote, like bigger than they should be, kind of rocking the boat of the Big Bang?
Well, I think, yeah, we're looking billions of light years into the past. And I think what you may be referring to or getting at is that there's seems to be some controversy that we're finding big galaxies early in time after the Big Bang, a few 100 million years after the Big Bang, that we didn't expect to see because our models of galaxy evolution suggest that there wasn't enough time for these galaxies to form within a few 100 million years. So there is some controversy about that, and we don't have it resolved yet, but that's a good thing. I mean, every time we put a new telescope up in space or even on Earth, we come up with answers, but we also come up with more questions. So there are always more questions, which I think is the way it should be.
Okay, we have time for maybe 2 more.
Hearing this lecture and seeing these pictures, I have been a climate activist for over a dozen years. I'm part of a group called the Fearless Grandmothers of Santa Barbara and other groups, and so we're working hard to transition away from fossil fuels. And so my question is, looking at the big macro of all of this, and if humans are causing now the 6th extinction, and we've had 5 and all this before, and all this life has, come back, does it matter in the scheme of things? Yes, we're going to be killing tons more species, and who knows about ourselves, but the planet is still going to survive, and maybe more life will evolve. I'm wondering, with all the work and this perspective, how do you place in context what's happening on this planet now?
Well, that's a big question. Not quite sure how to answer it, but it's possible, for example, that the reason we haven't found life already, although I doubt this is true, is that if life does exist out there on planets among other stars, exoplanets, maybe they get to the point that we're at now and they destroy themselves. And maybe life goes in cycles where when it gets too intelligent for its own good, it destroys itself, but you're right, the planet will still survive, and perhaps life will be created again, and something totally different will be created.
Give me 1 second before I give you your honorarium. There's an honorarium to take your gas home tonight. I got this incredible Chumash relic that we dug out off the side of the creek. It's worth priceless, and it's $10 if you want to buy one exactly like it. I just want to pay honor to some people. On the camera back there in the middle is our past president. Yeah, he's looking around. Tom Cotton, raise your hand. Chuck and Pat McPartland is our secretaries and our outreach and our merchandise. All of those sitting around them. Next Saturday night, you're all invited to the Star Party right here next door, I guess. Around the corner where the observatory is, 8 o'clock. Or come online earlier with us if you want to join the big meeting. And as I said, the next 2 first Fridays are booked. I'm still working on Friday, 1st of November, which I think is the 6th maybe, perhaps. I've got several calls out, but I have the 3 people in the club to do our December in-house show. In fact, 2 of them, one of them asking the questions, are sitting over there on the right. If you guys would raise your hand, Mike, and Earthquake Dave. Dave's going to talk about Chuck's specialty, but a different version of micrometeorites and different meteors. You got meteorites, right? You got a whole slideshow, right, Dave? And that'll be in December. And then Mike's owns 5 or 6 huge telescopes. He and his son get incredible pictures like you're seeing. What do you think these things are? Michio Kaku thinks they're big black holes. It's his latest theory.
He's a little bit out there.
He is, I know. He's way off on the edge. So without further ado, ladies and gentlemen, I'm going to call up the president to gavel this close. Incidentally, Bruce, is the president of the Santa Barbara Theater Organ Society. Those are the people that gather around the big, huge organ down at the Arlington. And if you have questions, raise your hand so anybody that wants to join your club can check with you on what's going on with the organs in the community. And please come and join our club, and we'll see you next Friday. You want to close the meeting, Mr. President? Jerry Wilson, who is a beloved friend of yours. Where did you guys work together?
We never actually worked directly together, but we had offices close by each other, and we knew each other.
In Hughes or Santa Barbara Research?
Santa Barbara Research Center.
Well, I'm going to get his version of that real fast. Is this why you were working in the Miri or before? It's called a Miri, right? M-I-R-I? When did you know this guy?
Oh, in the 80s and 90s, and around 2000, I transferred to what was used to be called the instrument division. Anyway, it became remote sensing.
You guys did hope you make it hard on Saturday night, didn't you? Last place out there. Thank you.
Thank you. Great job, Peter. This meeting is adjourned.
Just getting what?